Okay, in this video lecture, we're going to talk about bargaining and negotiations. Bargaining and negotiation are really central in a lot of business interactions. And you can think about negotiation and bargaining as really as a process to reach cooperation. So think about, for example, two firms that are structuring an alliance to develop a technology together. In that case, they have to negotiate the contribution of each firm to the project and also what to do with the technology once the technology is developed. A second way to think about negotiation is really a way to solve conflict. Even in terms of conflicts, there can be all sorts of conflicts that take place in a business environment. For example, there can be a conflict related to intellectual property and infringement of patents or copyrights or other intellectual property types. And this can be solved with litigation, but there can also be negotiation and bargaining between the firms involved in the dispute to try to settle the dispute and avoid costly outcomes in which judges and lawyers are involved. So we're going to see what type of models can be used to think about this type of scenarios, this type of negotiations. We're going to start with a very simple model that shows how time impatience, the time value for money essentially, matters in bargaining frameworks. And we're going to also see features of the bargaining environment that can generate delay and make the negotiation last a long period of time. One of these is going to be more of a behavioral channel, psychological channel. We're going to talk about overconfidence of the negotiators and show how in the presence of overconfidence you can have long delays in a negotiation. And the other is going to be more of an information channel. We're going to see that when parties don't have the same information, some party is more informed than others on particular features related to the negotiation, then agreement may not be reached, negotiation may break down, and this may lead to delays in reaching some form of agreement. Just a clarification before we start with the modeling. The modeling that I'm going to cover follows the tradition of non-cooperative game theory. More recently in strategy, a number of different models have been used to think about splitting values between parties. Some of these models involve concepts like the core or the Shapley value or Nash bargaining. Those are more what are called cooperative game theory. I'm not going to talk about this cooperative game theory in the video. I'm going to focus instead on the more traditional non-cooperative game theory approach. Okay, we're going to start our lecture with one of the most famous way to think about bargaining with a game theoretical perspective. This is come from the work of economist Ariel Rubinstein in a paper that was published in Econometrica in 1982. It's a classic paper. You can find simplified versions of this model in many textbooks of game theory and microeconomics. So in the model, there are two players, and we're going to call these players player 1, P1, and player 2, P2. And they have to split $1. Okay, the negotiation is about how to split $1. And the negotiation takes place over a number of periods of times. So you go from period 1 to period 2 to period 3 up to period capital T. we're going to assume for simplicity t is an odd number. Doesn't really matter. You can show, with slightly different math that the same is true if you have capital T that is even. But more importantly, we're also going to see what happens when t goes to infinity. Okay, that is also very useful in application. When you write papers of that usually assume some bargaining a la Rubinstein, you tend to think about the limit in which you have an infinite negotiation period. There is a discount factor equal to delta less than 1. Okay, this is the discount factor. And the idea of the discount factor is that for me to have $1 today is not the same as having $1 tomorrow. $1 in period 1 is not the same as $1 in period 2. $1 today is worth more than $1 in period 2. How much more? Well, that is driven by the discount factor. So $1 today is worth $1. $1 in period 2 is worth delta dollars. $1 in period 3 is worth delta squared dollars, and so on. So every time in the future we consider, essentially the dollar shrinks according to a discount factor equal to delta. Okay, that's the idea. So how is it this game works? Like, it works in a very simple way. So in period 1, t equal to 1, player 1 makes an offer. Let's call this offer x1 to player 2. And player 2 can accept or reject the offer. If the offer is accepted, then the dollar is split x1 for player 1 and 1 minus x1 for player 2. Otherwise, if the offer is rejected, we go to period 2. And in that case, player 2 makes the offer, offers x2 to player 1, and player 1 can accept or reject. If the offer is accepted, they're going to split the dollar according to x2, 1 minus x2. If the offer is rejected, we go to the third period. The third period, player 1 again offers x3 to player 2, and so on, up to the last period. Okay? In the last period, because it's odd, player 1 makes the offer, x capital T, to player 2. Again, player 2 can accept or reject. If it's accepted, the dollar is split x capital T, 1 minus x capital T. If it's rejected, the dollar essentially disappears and both players get nothing. Okay, that's the idea of Rubinstein bargaining game. Okay, so now to try to understand what is the solution of this game, let's start with an example in which there are only 3 periods. Okay, periods are period 3, period 2, and period 1. And let's think about what player 1 and player 2 get if the game reaches the final period. Okay, so if we get a period 3, player 1 is going to make the offer to player 2. Player 1 knows that the offer that it makes is the final offer, in the sense that if player 2 rejects, player 2 is going to get 0 because the dollar disappears. So in this situation, what we should expect is player 1 to essentially tell player 2, I'm gonna get the full dollar and you get nothing. Because if you reject this offer, you're gonna get nothing anyway. So there is no reason for me to offer you anything. By offering you nothing, I make you indifferent essentially between accepting and rejecting. So this is the assumed solution essentially at the last period. The player 1 gets the full dollar and player 2 gets nothing. Under the essentially player 2 is indifferent between accepting or rejecting this offer, and any kind of perturbation, any epsilon greater than 0 that can be offered to player 2 is going to be accepted. So this is the typical solution that people consider for the last, if we reach the last period. Now let's go to period 2. In period 2, player 2 is going to make the offer to player 1. You notice that by rejecting the offer, player 1 is going to get the dollar next time. So in order to make player 1 indifferent between accepting and rejecting the offer, I need to offer to player 1 at least delta, okay? Because $1 in period 3 for player 1 is equivalent to delta dollars in period 2. So delta is the offer that makes player 1 indifferent between accepting at time 2 or rejecting and getting the dollar play at period 3. So player 2, what is going to do is going to offer delta to player 1 and keep for themselves 1 minus delta. And it's going to be optimal for player 2 to do it because 1 minus delta is greater than 0, that is what is expected next period. So we should expect not to reach the last period. There is agreement in period 2, and the split is delta for player 1 and 1 minus delta for player 2, if we reach period 2. Now let's go back to period 1. So go backward. What we are doing here is what is called backward induction. We start from the end of the game and then we kind of reason backward. When we go to the first period, that is period 1, player 1 is going to make the offer to player 2. Player 1 does this reasoning and understand that if the offer is going to be rejected, player 2 is going to get 1 minus delta next period. So the minimum that should be offered to player 1, to player 2 to be accepted an offer at time 1 is going to be delta 1 minus delta. So player 2 is indifferent between receiving delta 1 minus delta in period 1 and 1 minus delta in period 2. Okay, because I need to discount by delta the value that I get tomorrow essentially. So this is the minimum that I can offer to player 2 to make the player accept the offer at the first period. And this offer is going to be accepted, and player 1 is thus going to get 1 minus delta times 1 minus delta. All the residual of the dollar is going to be kept for player 1. Okay? So this is essentially the solution of the 3-period bargaining game. We have two things. First of all, that the agreement is reached immediately, with player 2 getting delta times 1 minus delta, player 1 getting 1 minus delta times 1 minus delta. You don't reach the end of the game. There's never delay in this kind of environments. And second, how much is the split between these two depends on delta. As you can see, if delta is equal to 1, then in that case, the player 1 gets the full dollar, because this becomes equal to 0. Okay, 1 minus delta becomes equal to 0. So this delta times 1 minus delta is 0, and therefore player 1 gets the whole dollar. The idea is that for when delta is equal to 1, it means that the weighting is not important. So if weighting is not important, player 1 knows that is the one making the final offer, and therefore is going to get the full surplus at the end. Okay? Now, let's call V1 3, the payoff of player 1 in a bargaining game a la Rubinstein with 3 periods, okay? We have seen that this is equal to this, okay? It's equal to 1 minus delta times 1 minus delta. They can be written as 1 minus delta plus delta square. Now, if you do exactly the same table for any capital T odd, we said the capital T was odd, you can try an example with T equal to 5, with T equal to 7, and so on. You're going to see that you get payoffs that have exactly the same structure. Okay, they're going to be equal to 1 minus delta plus delta square minus delta cube and so on, plus delta capital T minus 1. Okay, so essentially they switch sign and they end with an exponent that is 1 minus the final period. Okay, so in this case was 3, the final exponent is 2. So for a generic T odd, the final exponent is capital T minus 1. Now, this is the fact that there is this structure here is really useful, because there is a result in mathematics that shows that if I take a number z that is in absolute value less than 1, okay, and I compute the summation for k equal to 0 to n of z with exponent k, I have that this summation is a convergent series, so it can be written in a kind of compact way as 1 minus z with exponent n plus 1 divided by 1 minus z. Okay? This is a result in mathematics about a convergent series. And why is it important for us this result? Well, this is important because what we have here is a summation. Is a summation of a z that is less than 1 in absolute value. If you set z equal to minus delta, you get that this is a summation of minus delta with exponent 0, with exponent 1, with exponent 2, with exponent 3, and so on. And the n, that is the final exponent, is equal to t, capital T minus 1. Okay? So this tells me that essentially this V1 of capital T, that is equal to the summation for k equal to 0 to capital T minus 1 of minus delta with exponent k, can be written as 1 minus z, so minus delta becomes plus delta, with exponent n plus 1, so n is t minus 1, it becomes exponent t, divided by 1 minus delta, that is 1 plus delta. Okay? So this gives me essentially the payoff of player 1 for a generic Rubinstein bargaining game that has t periods, and it is ending in a period that is odd. Okay? As I said, most of the application, if you assume that there is Rubinstein bargaining model, you set t that is equal to infinite. So what is the payoff here in the case of infinite? Well, if I take the limit as t that goes to infinite of v1t, I have essentially that this delta t with exponent infinite converges to 0 because it's a number that is less than 1, and therefore it goes to 0. And therefore this limit is 1 over 1 plus delta. Okay? So in a Rubinstein bargaining model with an infinite horizon, the dollar is split such that player 1 gets 1 over 1 plus delta, and player 2 gets delta over 1 plus delta. Okay, this is the payoff of player 1, and this is the payoff of player 2. This is just essentially 1 minus this. Okay, if I do 1 minus this, I get this one. The sum of these two is equal to 1. The dollar is split immediately. Even if there is an infinite horizon, you don't reach any period after period 1, that is the beginning of the game. And the split is equal to this split here. Now notice that if delta is equal to 1, the payoff is split half-half. If delta is equal to 0, the payoff is 1 for player 1 and 0 for player 2. So this delta, tells you that as the discount factor matters less and less, okay, as delta gets to 1 means that essentially $1 today is getting more and more similar to $1 tomorrow, then in this infinite negotiation, there is essentially similar bargaining power between the two players. And in that case, the dollar gets split with a similar amount. But as delta becomes closer to 0, it means that $1 today is worth much more than $1 tomorrow. And in that case, the first player, that is the player making the offer, is getting a larger fraction of the dollar. So this delta is a proxy of the time preferences, in which you have essentially an advantage for the first mover depending on the value of delta, and it's typically also assumed as a proxy for bargaining power of player 1. Okay, so if you have thinking about this as a negotiation between two firms, and you want to see what happens if the bargaining power of the first firm is greater and greater, you do comparative statics in delta, and you move delta from 1 to 0 essentially. Now, in practice, how do you use this model? Well, this is the split that you have in the case in which the two firms, the two players, have to split $1. If instead of $1 you have to split an amount of money equal to V, okay, V dollars, then the split that you should expect is V divided 1 plus delta for player 1 and delta V divided by 1 plus delta for player 2. So think about having V as really another formula that depends on all sorts of other variables. That is a value that two players in an industry or in whatever type of interaction that is of interest to strategy researchers generate. Then you can say, okay, I want to see how negotiation between these two parties may affect the split of this V. Well, a natural way to model the negotiation is really to assume Rubinstein negotiation and to say, okay, the first firm gets 1 divided by 1 plus delta, and the other gets delta V divided by 1 plus delta, and delta is a proxy for the bargaining power of the first firm. Okay? So this is the simplest model of negotiation. One important feature of the Rubinstein model is that there was never delay. Okay? There was always agreement at the first period. And this happens because essentially there is no reason to delay. Everybody knows how the game is going to evolve. You can predict exactly what happens at the end. You can predict what happens the period before the end and so on. And therefore, because you can predict at the first period exactly how things are going to evolve later on, you can find an agreement right away that avoids delay. We're going to move now towards a bit more sophisticated model of bargaining. a simple extension of the Rubinstein bargaining game, in which there is overconfidence, and I'm going to show you how to model overconfidence in bargaining. Here I follow an approach that was developed by an economist at MIT called Yildiz, Mohamed Yildiz, in a number of papers in the QJ and in Econometrica. And I show you how, if there is overconfidence for the player, if you enter into a negotiation, a bargaining negotiation with excessive overconfidence, excessive confidence on your bargaining power, that may create problems and generate delays. So to study this, we need to extend a Rubinstein model, adding some form of uncertainty, and then study what happens if there is disagreement on this uncertainty. Okay, so I want to consider a Rubinstein game with only 2 periods, and the game is it works in the following way. In the last period, in the first period, t equal to 1, player 1 makes an offer to player 2, and player 2 can accept or reject the offer. If the offer is rejected, we go to time 2. And in the Rubinstein model, a period 2 was player 2 making the offer to player 1. Now we assume that this is not the case, and there is some stochastic element here. With some probability, player 1 makes the offer, and some other probability, player 2 makes the offer. So with probability P, player 1 makes an offer again to player 2, and the offers can be accepted or rejected. And with probability 1 minus P, player 2 makes the offer to player 1. That also can accept or reject the offer. If the offer is rejecting player 2, the game ends. So they both get 0. Now, instead of assuming that you split $1, let's assume that you split V, a value V, just to make it a bit more general. Okay? Now, let's study what happens in this game. Okay? Now, let's assume that player 1 makes an offer to player 2 in the first period, and player 2 rejects the offer. Okay? So if player 2 rejects at t equal to 1, then player 2 knows that next period the player can get the full value V if the player is the one making the offer. But this is not something that happens for certain. This happens with probability 1 minus P. Okay? So the expected value in period 2 for the player 2 is V times 1 minus P multiplied by delta, because from the perspective of period 1, $1 in period 2 is worth delta. Okay? So the idea of the player 2 is making this reasoning: if I reject the offer the player 1 makes, next period I can get the full V if I make the offer. The full V is worth delta V today for me, because $1 tomorrow is not the same as $1 today. But this happens only with probability 1 minus P, in which I can make the last offer and appropriate the old value. With probability P, player 1 is going to make the offer next period, and I'm going to get 0. See? So the expectation for the player in period 1 by rejecting the offer is to get in the next period delta V times 1 minus P. So player 1 at period 1 offers to player 2 V minus delta V 1 minus P. Okay? Essentially, I transfer to, I let player 2 get all what is expected to get if he rejects the offer. I make player 2 exactly indifferent between rejecting and rejecting the offer in period 1, and I get all the rest, okay? So this means that, in this situation, this is the payoff that I should expect for player 1 in period 1 if there is an offer made and accepted by player 2, that is accepted by player 2. Player 1 may say, okay, what if I delay the offer? Okay, what if I make an offer to player 2 that is a crazy offer? I offer player 2 very little, so the player 2 is going to reject. What is the expected payoff of player 1 if the game reaches time 2? Well, if the game reaches time 2, player 1 is going to get V if player 1 makes the offer, that happens with probability P. And this is going to be reached next period. So from the perspective of time 1, this has to be discounted by delta. So what it means is that immediate agreement is better than delay for player 1 if V minus delta V times 1 minus P is greater than delta VP. It means, you can rewrite these things as V has to be greater than delta V times 1 minus P plus P. That essentially can be written as V is greater than delta V. That is satisfied because delta is strictly less than 1. Okay? So, what is the lesson here? The first lesson is that even if there is a stochastic element, okay, that player 1 doesn't know at time 1 who is going to make the offer next period, that stochastic element doesn't matter. It says that you're going to have agreement in the first period. It's not generating delay. And it's not generating delay because the two players essentially agree on the uncertainty. They have exactly the same perception of the uncertainty. They agree that next period, with probability P, player 1 makes the offer, and probability 1 minus P, player 2 makes the offer. Now I want to introduce overconfidence in this little model. How do you introduce overconfidence? Well, remember what we said, what happens in period 2. In period 2, player 1 makes the offer with probability P, right? And let's assume that there is a disagreement between the two players. Player 1 thinks that P is equal to P1, and player 2 thinks that the probability is equal to P2, with P1 strictly greater than P2. Okay? The idea is that the difference between the perceived probability of P by firm 1 and firm 2, or player 1 and player 2, is a proxy for optimism of player 1. So from the perception of player 2, if you're player 2 you think the P is equal to, for example, half, and player 1 says no, is equal to 3/4, you think that player 1 is overestimating their bargaining power. It's saying, okay, you think you are making the offer with a much higher probability than is actually the real probability, or the probability that I think it is. Okay, so this difference P1 minus P2, we're gonna call it O upper bar, is the optimism or overconfidence. Okay, in the negotiation. And this is the trick that has been used by Yildiz to incorporate essentially overconfidence in the negotiation. So this is important because it means that by rejecting the offer, at t equal to 1, P2 expects a payoff equal to delta V times 1 minus P2. So player 2, I know that if I don't accept the offer for player 1, then next period I'm going to make the offer with probability 1 minus P2. That's the probability I think is the one that I'm going to end up making the offer. And I'm going to get the full V at that time, that from today's point of view is worth delta V. So it means that to have immediate agreement, P1 has to offer at t equal to 1 this amount to player 2 to get a payoff equal to V minus delta V times 1 minus P2. So if I know that I have to offer this one to player 2 in order to make sure that player 2 doesn't delay the agreement, then the payoff that I can get in the absence of delay is V minus this thing. Now, by delaying, so if I make an offer to player 2 that is much less than this, player 2 is going to reject. So by delaying, player 1 expects delta V P1. Okay, if I delay, if I make an offer that player 2 doesn't accept, then next period I'm the one making the offer again with probability P1. This is the probability that I think is the right probability as player 1. And I'm going to get the full V, but I'm going to get in next period, so it has to be discounted by delta. So it means here that to delay is profitable if delta Vp1 exceeds V minus delta V 1 minus P2. If this is satisfied, then I'm better off actually as a player 1 to delay, to make an offer in the first period that is rejected and having an agreement in the next period. How do I get to this? This thing can be written as delta V P1 minus P2 plus 1 has to be greater than V. V and V here simplifies. P1 minus P2, we said we call it O as a measure of overconfidence, plus 1 has to be greater than 1 over delta, or gives me the finding that O has to be strictly greater than 1 minus delta minus 1. So interestingly, here it shows you that essentially if there is enough optimism, if there are enough divergent expectations between player 1 and player 2, I may end up having delays. Okay? And this is one reason why you can get delays in negotiations. You may have data in your, for your research that look at interaction between firms, and in some cases, the interaction, leads to an agreement right away. In other cases, is an agreement with delay. What can be a source of delay is disagreement between firms. As you can see, if the disagreement is large enough, if the optimism is large enough, there is not agreement immediately. Why this is the case? Well, because firm 1 thinks that firm 2 is overconfident. Firm 2 thinks that is making an offer next period with a probability that is way bigger than the probability of firm 1 thinks is the right probability. To reach agreement immediately means that I have to offer quite a lot to firm 2, because I have to offer an offer that is related to the perceived probability that firm 2 has to make the offer in the next period. So I'm better off not making an offer that is accepted right away. It's too costly to have an offer accepted right away, because I have to make an offer that matches this perception of player 2 that is overconfidence in my view. And by delaying, I can essentially get what I get in the next period that depends on my perception of my bargaining power next period, that it can be substantially different and substantially greater, especially if the difference between the two probability is large. So we saw this condition for overconfidence to generate delay. This gives you a nice intuition of why, hopefully with the simple model that I show you, a nice intuition of why overconfidence can generate delay. One problem with this formulation that is not the best formulation to have a practical application in an empirical analysis is because it doesn't depend on V, okay? V simplifies away. And a lot of time, you have information in your data of how long it took to negotiate an agreement, but you have also information on the type of the agreement, okay, and the value generated by this agreement. So it would be nicer to have a formula that tells you when there is delay that depends not only of the discount factor, but also tells you how is that the value V may affect or not delay. So there is a simple way in which you can extend the two-period model that I show you to have actually the delay depending on V. And the idea is that we can assume that if you reach period 2, and you are the one making an offer, you're not making the offer on a total amount equal to V, but you make an offer on an amount that is a bit smaller, and we call it V minus little l. Where little l, I like to think about it as, fees for a lawyer, okay? So the idea is that you can start a negotiation with a customer, for example. The negotiation breaks down. There is some uncertainty on what you're gonna get next period. That uncertainty is related to this probability P1 and P2. But next period also you have to pay some extra cost in order to reach the agreement. For example, you have to pay some money to lawyers to negotiate a settlement of some sort, or to draft a contract that is much more complete and can be enforced in court. So in this case, what I need to offer to player 2 to have agreement next period, to have agreement immediately for player 1, is 1 minus P2 delta times V minus L. And this means that player 1 with kind of an immediate agreement is going to get V minus this thing here, okay? And with delay, player 1 gets P1 delta times V minus L. This is essentially the condition that we had before, with the only difference that I subtract delta to V, L to V, in the second, if we reach the second period. Okay, so if I agree immediately, then this is my payoff of player 1, V minus what I need to offer to player 2 in order to convince the player to get an immediate agreement. And if I delay, this is what I get. I need by making the offer essentially next period. Now, this can be rewritten as delta times V minus L times 1 minus plus P1 minus P2 has to be greater than V. So delta, now V minus L times 1 plus O bar has to be greater than capital V. As you can see now, I cannot simplify the 2V because here is V and here is V minus L. So I cannot simplify the two as I did before. So now it's actually a function of V, the solution. So this says that 1 plus O bar has to be greater than V divided by delta times V minus L, or O bar has to be greater than V divided by delta times V minus L minus 1. Okay, as you can see now, the condition to have this agreement leading to delay depends on V. And as you can see here, if you take the derivative of this thing respect to V, you can see that actually this is decreasing in V. So as V gets larger and larger, this thing gets smaller and smaller essentially, and eventually you can have that for V small there is not disagreement, and for V large you have disagreement. Okay, so delay is more likely with high V, but this essentially helps you if you have a formula for V that can be mapped especially to an empirical application, and you can then do comparative statics on the formulas of V to see whether essentially the threshold here to have disagreement gets larger or smaller. The next thing that I want to cover is negotiation over the settlement of a litigation. That is a model that can be used to study a number of interactions in strategy where there is actual litigation, for example, patent litigation, in which you have data on, for example, how long it took to settle the litigation and whether there is delay or not in settling a case. But in general, it's a nice setting to study how is the negotiation with incomplete information can generate delay when one party knows stuff then the other party doesn't. Okay, so it's a nice illustration of how asymmetric information can generate delay in bargaining. So we have a two-period model, and this is a simplified version of a more sophisticated model in a paper by Catherine Spear. And also there is work, similar work done by another law and economics scholar called Babchuk. These are like classic model of settlement of litigation, and this is a simplified version to kind of that I think can be very natural to use in applied setting. So there are two parties. We call the first party player 1 and the second party player 2. player 1 make an offer of a settlement, and we call this offer capital S, to player 2. And player 2 can accept or reject the offer. If the offer is accepted, then they split a value according to the settlement deal, V minus F to player 1 and S to player 2. If they reject, they go to court. And there is essentially a judge that decides how this V is going to be split. It's going to be split in the following way. With probability 1 minus P, firm 1 gets the whole V. And with probability P, firm 2 gets the full V. Minus, though, litigation cost. So both firm 1 and firm 2 have to pay a litigation cost, their own lawyer. This P essentially is the probability that player 2 wins, okay? So think about player 2 has a patent, and player 2 can win only if the patent is found to be valid, it's found to be infringed. And this is something that player 2 needs in order to be successful. But there is asymmetric information. So player 2, we assume that knows the right value of P, the precise value of P, whereas player 1 only knows that P is distributed uniformly over an interval 0, 1. So player 1, I really don't know how strong this patent is, how strong my case is to say that there is no infringement. I just have some expectation that there can be a distribution. That, you know, the more general models here, they consider just more sophisticated distribution probability. You assume that it's just uniform to make the case more tractable. Okay? So there is a symmetric of information, as you can see. Player 1 doesn't know this P. He just knows the distribution. Whereas player 2 does know the P. And therefore, there is asymmetric information. And we're going to see that this asymmetric information is actually going to be very important. It can be a source of delay and absence of settlement, essentially, and you reach the litigation. So, let's try to think through this scenario. So, player 2 is going to accept an offer S only if this S the player 1 offers is greater or equal than what player 2 can get with the litigation, that is PV minus L2. This can be rewritten as P as to be less or equal than S plus L2 divided by V. Okay? And we're going to call this formula here P wiggle. And as you can see, this P wiggle essentially gives you a cutoff, okay? If you think about P going from 0 to 1, P wiggle here is the cutoff that tells you that if the P of player 2 is below P wiggle, then the player is going to accept. If the P is above P wiggle, the player is going to reject. So the idea is that when I make an offer for a settlement, who is going to accept this offer? Well, those that are going to accept this offer are those that probably are going to get less than the offer in court the next period. So those with not a strong case. But those that have a very strong case and they think that my offer is too little, they're going to reject the offer and go to court and litigate. Okay? So any settlement offer essentially can be thought as picking a threshold that tells me how many, how many player 2 are going to accept and how many player 1 player 2 are going to reject. Okay, what is the probability sense of a reject and an accept? So if you think about player 1 now, the expected payoff of player 1, we're going to call it capital P wiggle, by offering a settlement that creates a cutoff equal to P wiggle, is equal to the following. So for the types that go from 0 to P wiggle, player 1 is going to settle right away. So it's going to get the full value minus what is paid in terms of settlement, that is P wiggle minus P wiggle times V minus L2, okay, dx. For the P that goes from P wiggle to 1, the settlement is not going to be accepted. It's going to go to court, and player 1 will get V minus XV minus L1 times dx. Okay, so here there is also a parenthesis. That tells me that, you know, it's going to be determined by court, and that depends really on the actual probability that the player 2 is kind of winning in court. Okay, so this depends on the actual probability. This one essentially does not, because all these, independently of the actual probability, all the people that have a P below P wiggle are going to accept the settlement. So now let me solve this integral here for this formula. Now you have to take to find the formula for which the derivative respect to x is equal to this, and the derivative respect to s is equal to this. So here from 0 to P wiggle, this thing is Vx minus P wiggle x plus L2x plus, and here we go from P wiggle to 1 is equal to Vx minus x squared divided by 2V minus L1x. Okay, so if you take the derivative of this respect to x is equal to this one, take the derivative of this respect to s is equal to this one, and this is what matters from 0 to P wiggle, and this is what matters from P wiggle to 1. Okay. Okay, this is what we need to solve now to have the profit of the firm 1 given an offer that has a cutoff of P wiggle. Notice that here is P wiggle x V. This V was missing in the previous page, so that was needs to be corrected. But this is equal to V P wiggle minus P wiggle square V plus L2 P wiggle. So it's this thing evaluated at P wiggle minus this thing evaluated at 0, that goes away, plus this thing evaluated at 1, that is V minus V divided by 2 minus L1, minus these things evaluated at P wiggle, that is minus V P wiggle minus, and becomes plus P wiggle square divided by 2V plus L1 P wiggle. Now as you can see, I have a P wiggle here and a P wiggle V and P wiggle V here that simplifies. Here I have P square V and P square V divided by 2 that also can be summed together. So this is equal to V over 2 minus L1 plus P wiggle L1 plus L2 minus P wiggle square divided by 2V. Okay, this is the profit that the first player makes if it makes an offer of settlement that is associated with a cutoff for acceptance of the offer equal to P wiggle. So now the question is the following. What is the optimal offer that I should make as player 1? Well, the offer is the one that maximizes the profit. Okay, you have to find a P wiggle that maximizes the profit. How do I find this? Is by taking the derivative respect to P wiggle and set it equal to 0. So the derivative of this is 0. The derivative of this is L1 plus L2. And the derivative of this thing here is P wiggle V. This is to be equal to 0. And this gives me the optimal P wiggle star. That is L1 plus L2 divided by V. So it tells you essentially that the optimal cutoff depends on two things. Depends on the litigation cost. Is higher, the higher are the litigation cost. And on value is lower, the greater is the value at stake in the negotiation. Now, in a lot of empirical work, you have data on delay. For example, you have data on litigation. You know when the litigation starts and you know when the litigation is settled. And you would like to kind of try to figure out how that changes in V and L may affect the delay of the settlement of the litigation. Now, this formula can help you. Remember that this was a simple two-period model and that you had immediate agreement. Okay, you have settlement at t equal to 0 for P that was less than P wiggles. So in this case, less than P wiggle star. And you had delay if P was greater than P wiggle star. So now we also know that P is distributed uniformly. So the expected time in which this dispute essentially is going to be settled and decided and terminated is equal to period 0 for the probability that P is less than P wiggle star and equal to period 1 for the probability that P is greater or equal than P wiggle star. So in expectation, I have 0 with the probability that P is below P wiggle star and 1 with the probability that P is greater than P wiggle star. So this thing kind of simplifies, is equal to 0 because you multiply to 0. And this is because of the uniform distribution, the probability that P is greater than P wiggle star because of the uniform distribution is equal to 1 minus the cumulative of P wiggle star, that in the uniform case is just equal to P wiggle star. So in other words, this model, in this simple model, there is an expected delay in the negotiation, the expected time in which essentially the negotiation concludes, that is equal to 1 minus L1 plus L2 divided by V. It is a very nice kind of comparative statics in the sense that the greater are the litigation cost, the more likely is that you have the T small. The more expensive is to pay lawyers to have matter resolved in court, the more likely is that you kind of solve the disagreement early without having to use lawyers. On the other hand, when the value at stake is large, especially is large relative to the litigation cost, then it's more likely that litigation takes longer to be settled. Okay? So this is a natural formula to use in applied settings. If if you have a set data on delay in litigation, and you have some theory that tells you that the value of stake in the litigation depends on all sorts of parameters, you can see how changing this parameter changes V, and changing V changes the time of expected settlement, okay? So this is natural to kind of guide testable hypotheses on the settlement of